Hey everybody, it's Professor Gibbons. I'm back to talk to you some more for our asynchronous class. I want to talk about chapter 9 in our textbook. This is new material and it gets into these things called principal ideal domains. Now, we've heard the word domains before in the context of integral domains, but we haven't heard the word ideal and we haven't heard the word principal yet. So we're going to unpack this idea of this thing called a principal ideal domain in a few steps. And that's what we're going to start with today. And we'll wrap this up later this week. So this is chapter 9, principal with an AL. This is a principal as an adjective, ideal domains. And here domains is indeed short for integral domains. So all of the axioms that an integral domain should satisfy, these things are also going to satisfy, plus a few extra things. So I want to start by reminding us of an example. I've got the even integers. That's a subset of the integers. In fact, it's also a subring of the integers. And the way that we would check is we would use the subring theorem, which I will remind you about. So the subring theorem says check that it's non-empty. Okay, 2 is in there. Also 0 is in there. Also negative 42 is in there. We've got lots of things in there. It should be closed under addition. And we could verify that if I take an even number like 2n and I add it to an even number like 2m, I get 2m plus n, which is also even. So this is just a fancy way of saying even plus even is even. It should be closed under additive inverses, which is really closed under subtraction. And that's the same thing's going to work. If I look for the additive inverse of 2n, it's really just 2 times negative n. So that's still even. So the additive inverses are in here. And then closed under multiplication. And in fact, if I take 2n and 2m and I multiply them together, it's a multiple of 2, but even more, it's a multiple of 4. So like I actually sort of have an extra 2. I could have just, like multiplied by any integer and it would still be even. So this is saying even times even is still even. And so it satisfies all of the 4 things that we need from the subring theorem. It's not going to be a field. Z is not a field, but also 2z isn't a field. Both of them fail because we don't have multiplicative inverses. So this observation that we have an extra 2 in here, right? That this guy is extra, might motivate us to kind of relax the idea of what kind of multiplication we care about. And so let me make this next definition. And we will see if this relaxing how many 2's we need satisfies this definition. So let's say that an ideal I of a ring R is a subring of R satisfying the additional property for all R in R, for all A in I, RA is in I and AR is in I. And I'm going to name this property. Our book doesn't name it, but I'm going to. I'm going to call this SM for scalar multiplication, where the scalar comes from the ring R and the A comes from our ideal I. This kind of reminds me of vector multiplication, right? You take something from, your field and you multiply a vector by it and you're scaling it and that lands back in your vector space. This is a really similar property. It's like we're taking something from the ideal and we want to make sure if we scale it by something in the bigger ring, we still land back in the ideal. So scalar multiplication is one way that you can parse this SM. Some people call this strong multiplication. It's closed under strong multiplication, where you're saying like not just I and I should land back in A, but the stronger assumption that R and I, when I multiply those kinds of things together, I get something back in I. And the last phrase that sometimes you hear used is multiplicative absorption, which to me, absorption, I'm not sure that I can spell it. It sounds a little gross. Like it sort of sounds like we're advertising diapers or something. Like it's got huge absorptive properties, but it is. It's again, it's like I absorbs products when you multiply by something from R. So you could sort of, I don't know, if you like a visceral mathematics, you can think of it as like. When we come back together, I'm going to get the Legos that the dean bought me, and I'm going to demonstrate some of these ideas with Legos. So please hold tight for that. We'll mess around with these ideas together when you can ask questions of me in person. But just know that the Legos are coming soon, and we're going to talk about ideals using Legos. So some examples of ideals. Well, it turns out that the even integers within the integers, it is a subring. We checked that. So we just need to check that strong multiplication holds, or scalar multiplication holds. And this is saying if I take an element of my ideal, which looks like 2n, and I multiply it by anything from my integers, like k, what I get when I do that is 2nk. That's the same thing as 2n times k. And all of those land back into z because they're still even. So if I take an even integer and multiply by an integer, I still have an even integer. And that's why it satisfies that strong multiplication property. So in fact, 2z is an ideal of the integers. And it has a really kind of quick name. We could say it's the ideal of integers divisible by 2. And you can actually take any integer that you like. I could look at, 18z, which is the set of things that look like 18 times n for some n in z, is also an ideal of the integers. And I'll let you check that. It's going to look really similar. We'll use the subring theorem and then strong multiplication. We'll check that. And in fact, it's the ideal of integers divisible by 18. Right? So anything divisible by 18 lands in this set. And if I multiply something divisible by 18 by any other integer, it's still divisible by 18. So strong multiplication holds. And you can check if I add two multiples of 18, I can factor in 18 out. So that's good. If I want the additive inverse, just multiply by -1. So you might believe, without going through all the details, that this is actually a subring of, or as an ideal and a subring of the integers. Let's look at some more examples, and let's look at, in fact, a non-example. So if I take the integers as a subring of the rational numbers, so we have a subring, but not an ideal. I'll let you verify the subring theorem, but to show that it's not an ideal, if I take 2 in the integers, and if I take, and this is not an ideal of the rationals, if I take 1/3 in the rationals, the product 2/3 is not in the integers, right? So it fails that strong multiplication. The same thing happens if we do something like Q is a subring of R. If I multiply a rational number by pi, that's a legal thing I could multiply it by in R, but it doesn't belong to the rational numbers when I do the multiplication. So proposition 9.2 says, I think of this as the ideal theorem. If you want to show something as an ideal, you could say a subset I contained in a ring R is an ideal of R if and only if, we're going to get four things here. They're the first three things from the subring theorem. And then the last one, we just replace the multiplication with the stronger multiplication. So we have I shouldn't be empty. We have that if I have a pair of elements, x, y, and I, then x plus y should be an I. If x is an I, that should tell me that negative x is an I. And x in I and r in r should tell me that xr is an I and rx is an I. I'm specifically allowing for the possibility that this is a non-commutative ring, in which case we have to check both factors or both products. If it's commutative, then xr and rx are the same thing. We don't need to check both. All right, so I want to leave you with a bit of a cliffhanger that we'll pick up with next time. R is a ring. 0 is a subring of R. So whatever R is, 0 is the 0 element from R, and I'm taking the set that just contains that. So I think you should probably check this. I also have that R is a subring of itself. Well, it satisfies all the ring axioms. And so as a subset of itself, it still satisfies all the ring axioms with the same operations. So just from the definition, we know that this is true. So this comes right from the definition. It's a subset that's a ring under the same operations. Well, R is a subset of itself, and it's a ring because we already assumed it was. But also, these are even more, they're also ideals. So, and an ideal of R for both of these. And so once you check it's a subring, you just check one more thing to check that it's an ideal. And because every ring has these ideals, they're kind of boring. It's like if I hand you a ring, you're like, and I ask you for the ideals, you're like, well, I know 2 off the top of my head. As you know, if the ring's non-zero, then the whole ring and the 0 thing, those are 2 ideals right away. So because every ring has these ideals, we call them trivial. Not because they're like easy or I don't know, like sometimes I feel like trivial is a little bit of a slur in mathematics, but what I really mean is that every ring has them. They're guaranteed to be there. So when we ask about what ideals does a ring have, usually we're asking what other ideals does a ring have? What interesting non-guaranteed for every ring ideals does something have? So when we ask for non-trivial ideals, we're saying, let's exclude the ones that all rings have, the ring itself and the set that contains only 0. I said that was a cliffhanger. So here's the real cliffhanger. How do we know if an ideal I is actually just the ring R in disguise? Right? So maybe I've given you something that looks like it's a subset, but I don't know that it's not the whole ring. And I want to know, is there a way that we could check that? So that's what we're going to pick up with next time. We're going to talk about what happens specifically for rings with unity. So at this point in this video, in this little short video, we've talked about the word ideal. We haven't yet hit on the word principal, and we're going to talk about that together in class on Friday. All right, that concludes your videos for Wednesday's class. And if I use this in future years, I hope the dates line up okay. But anyway, in 2021, this was a Wednesday class. All right, let me quit recording and I will see you in office hours tomorrow or on Thursday.